Hello, I'm Papia. In this problem, we have the value of cosine of 0.3 is approximated by this given polynomial, the Taylor polynomial. We have to first use the Taylor's theorem to obtain an upper bound for the error of this approximation, and then we have to calculate the exact value of the error. So recall, from Taylor's theorem, we can figure out the remainder, or Rnx. And the formula is, it is the n plus 1th derivative of the function evaluated at z divided by n plus 1 factorial times x minus c to the power n plus 1, where this z lies between x and c. So in order to calculate error is nothing but absolute value of Rnx. Okay, so that's what we have to figure out. You just take the absolute value. Now, we need to only find an upper bound for this error. So first, we have to figure out all these different variables from the given information and then see if we can compute an upper bound. Okay, so let's see what is given to us. We need the function. So the function is cosine of x. All right. We need x. What is the value? Well, 0.3 is x. So what is the center c? Look, from the Taylor polynomial, the center is 0. And what is n? Well, again, from the polynomial, the highest degree, n, is 4. So we have everything, and we also know that z will lie between these two values, 0 and 0.3. Okay, so let's plug everything in this formula. So we have Rn, n is 4, R4, and x is 0.3. Right here is f to the power, or the derivative is n plus 1th derivative. N is 4, so n plus 1 means it's the 5th derivative. And we'll figure it out in a little bit. The next term is x minus c. Well, x is 0.3, c is 0, so this is 0.3 to the power n plus 1, so that's 5. And you divide by n plus 1, which is also 5 factorial. So we can figure out the upper bound as soon as we know what is the 5th derivative of the function evaluated at z. Note, z lies between 0 and 0.3. Okay, so let's think about the derivative of this function. Well, what is the 5th derivative of cosine? Now you can keep on taking the derivatives, right? The first, second, and so on. But notice that every time you take the derivatives of cosine, it will either be a positive sign, a negative sign, or a positive cosine and a negative cosine, whatever derivative you take. So in particular, we can quickly do this. Let's see, f prime is negative sine. F double prime is negative cosine. F triple prime will be positive sine. F4 will be cosine. And then F5, the one we want, is going to be negative sine. Okay, so the 5th derivative is a negative sine. Now we want to figure out a maximum value of that derivative at z. Okay, so let's start by taking the absolute value both sides first. So this is equal to absolute 5th derivative at z. And then you don't need absolute value for the numbers because they're already positive. 5 factorial. Okay, so the fifth derivative is negative sign with absolute value. You can get rid of the negatives. So it will be absolute sine of z times 0.3 to the 5 over 5 factorial. Okay, z lies between 0 and 0.3. So do we know a upper bound for sine of z? Yes, we do. Sine is always less or equal to 1. So we get an upper bound there, and then you multiply the constants. And therefore, we have an upper bound for our error. Well, let's use a graphing utility to figure out what this upper bound is. Well, this is approximately 2.03 times 10 to the power -5. Okay, so the second part of this problem is we have to calculate the exact value of the error. Now, what is the exact value of the error? Well, look at our given information at the top. Cosine of 0.3 is the actual value and is approximated by this polynomial. So you subtract the two values and take absolute value because we need the error to be positive, and then you will get your exact value of the error. So the exact value will be absolute of the difference between cosine of 0.3 and the right-hand side, which is 1 minus 0.3 square over 2 factorial plus 0.3 to the 4 over 4 factorial. Okay, so let's plug it in our graphing utility again. And so the answer is 0.000001. So this is the exact value of the error. Thank you.